Hi, second try. We're going to talk about Fermat and the so-called method of adequality. And okay, I just did this in class today, but it was the worst explanation I've ever given of this. It was really quite terrible. So let's have a second try. Okay, so first of all, there's this ancient problem, and this ancient problem, which was completely, known to the ancient Greeks, and also totally solved by them, is this problem, a geometric problem, of given some segment of length b, so this segment is of length b, divide the segment up into two pieces such that the product of the pieces is equal to some other segment, or rather some area maybe. So okay, so if this is x and this is b minus x, then I want to construct the rectangle, sort of x times b minus x, such that this is equal to some other rectangle, some given rectangle. So there's some, or maybe even it's a square or something, and the area of the square is c. So okay, I won't get into the geometry of this now, but if you're Euclid, then there's an entire procedure, which is a construction with straight edge and compass, which can solve this problem. And in fact, the ancient Greeks did solve all of their so-called quadratic equations, the kind of things that the Babylonians did solve equations like this, simple quadratic equations. They solved them all via geometric construction, or at least they justified them all via geometric construction. Okay, so solving this is sort of easy, and okay, it's just easy. In a modern view, you can just multiply through, and you get bx minus x squared equals c. And so really we're trying to solve the equation x squared minus x squared minus bx plus c equals 0. And this is just not a hard equation to solve. And everything will be great. Okay, okay, sounds good. So you just do it and that's it. Maybe we can sort of think of this by talking about some sort of function. This is now a modern view, but okay. So take the function x squared minus bx. And then what we really are sort of saying to ourselves is, when is f of x equal to c? So we're sort of solving this equation. Okay, well, viewed this way, of course, I can just graph this function. What's it going to look like? Have I done something kind of weird here? Okay. Maybe it's best if we don't do it like this. Maybe it's best if we sort of leave it in its original formulation. So that would be this one. In its original formulation, we have x times b minus x that we want to be c. That's the original geometric formulation. So maybe what's best to do is to just let that be the function. So let the function be x b minus x. And now we are asking the question, for what values of x does this equal c? So solving this equation. And like I said, we already know how to do this. Let's try to understand this graphically. And okay, so here is this quadratic. It's pretty simple. There's a root at 0. There is a root at b. And what does it look like? It's an upside down quadratic, so it looks like that. I'll just draw the positive stuff because that's what Fermat would have done. And then, this is the part that I explained very, very poorly in class, and hopefully I'm explaining it better now. Take this line, y equals c, and therefore, I can conceive of what I'm doing as, finding the intersections of this line with this parabola, and okay, we can call this, there are going to be always two roots, and the two roots are x1 and x2. They're the two numbers which are solutions to this problem. And of course this problem has two solutions because whatever x is, then b minus x will also be a solution. So in fact, there's kind of an obvious relationship between these two solutions, the obvious relationship between the two solutions to this geometry problem is that x1 plus x2 is just b. Because once you find the piece, then you get the other piece. Well, the product of the two pieces has to be c, and so it doesn't matter which piece you find. The other one is just going to be b minus that. Okay, hopefully that makes sense. Okay, and now Fermat's just kind of screwing around here, and he's saying, okay, well, now that I have this kind of picture of everything, I wonder now, let's change the problem slightly. This is what I think was confusing about this and what I explained very poorly in class. Instead of being given a fixed area C and being asked to split the segment up into two pieces such that the product is C, now let's just kind of figure out, hey, how much area can I get at most? And okay, it's just obvious from intuition, common sense, thinking about it for a couple seconds or whatever, as people said in class, that you get the most area by cutting the segment in half. That's just kind of a basic problem about maximizing area of a rectangle for a given perimeter. You want it to be as square-like as possible. Okay, so that's of course true. But here, said Fermat, sort of emboldened by this sort of increase in algebraic sophistication that was happening, he said, okay, well, let me now sort of think of myself as moving the blue line kind of up and down, and when do I acquire a maximum? So that's now the question. Let me sort of draw a line here, and the answer is sort of when is C a maximum is the question. And okay, well, one can just see by looking at it that C is going to be a maximum when you move these 2 points x1 and x2 sort of infinitely close together. And so if you continue to move, and I'll draw my dotted line. This is now a new value of C. Call it like, C prime or something. Now, when C prime is getting to be very, very big, what happens is the two points of intersection move kind of infinitely close together, and so the highest value of C will occur when the two numbers x1 and x2 are just equal to each other. Okay, well that's kind of interesting, and then Fermat says, okay, well, suppose what are some properties of these two roots? Maybe it was actually better to do this sort of fact first, because well, it's true for both of these roots, x1 and x2, that f of x1 is c, of course, and that f of x2 is c. Okay, so what does that tell me? It tells me that bx1 minus x1 squared equals bx2 minus x2 squared. Okay, which is just another way of saying that, well, perhaps maybe I'll just even introduce one more step here, which is bx1 minus x1 squared is c, that's a fact. And it's also true that bx2 minus x2 squared is c. And so I can set them equal to each other. And when I do that, I get bx1 minus x1 squared equals bx2 minus x2 squared. And then we can move things around a little bit. So let's see, I think I want to do like this. So I get x2 squared minus x1 squared equals x2 minus bx1. This is just algebra 1 going on here. Now I can factor this, x2 minus x1, x2 plus x1 equals bx2 minus x1. And now I can just divide by x2 minus x1. And let's dwell on that for sort of a second, because that's a key sort of step. But it's algebra, so maybe it's better if you sort of don't think about it. What do we find? We find that b is x1 plus x2. Alright, we appear to be going maybe like round and round in circles or something like that, because I already told you over here that it was sort of obvious that x1 plus x2 was b, based on the sort of geometry of it. But now, here we have sort of an algebraic technique which also confirms it. And this was also known to Vieta and all the people who were reading Vieta, which includes Fermat, that given any quadratic equation, after all, the quadratic under discussion is the quadratic which we would now write as negative x squared plus bx. And if we factored out the leading coefficient, which one does when one is trying to apply Vieta's formula, we know that the coefficient of the linear term is the opposite of the sum of the roots. And so it is problems like this that Vieta investigated. He wanted to encourage mathematicians. This is Vieta's formula, which we learn in Precalc A and Precalc C, that the sum of the roots of any polynomial is the coefficient over here if it's a quadratic, once you factor out the leading coefficient. Okay, maybe you forgot this, but anyway, here's sort of 3 different proofs of this fact. Okay, so says Fermat now, look, this is just a fact about this particular function. A fact about this particular function is that when I'm solving for the places where this function equals c, for any c, that I always get 2 roots, and the fact is that when you add those 2 roots together, you get this number b. If that's always true, that when I add the 2 roots together I get b, then says Fermat, back to this problem, if I want to know where c is as big as possible, well, c is as big as possible when x1 equals x2. So to answer this question now, c is a maximum answer when x1 equals x2. Okay, and so let's just set x1 equal to x2. Let's just call that x. Okay, for the moment. Well, then what do I know? Since x1 plus x2 is b, I conclude that in fact just x plus x is b. And therefore 2x is b, and so x is b over 2. Okay, what just happened here was a proof of the fact that if you want to make c a maximum, then you should bisect the segment. But what we've now done is we've sort of left the geometry behind entirely. We're no longer going to be inspired by the geometry or care about the geometry. We're going to just focus entirely on the algebra. And one may sort of erase all of this kind of thinking and erase the geometric origins of the problem and just say, hey, I got this polynomial. When is this polynomial as big as possible? It's as big as possible when the sort of solutions to the points of intersection are on top of each other. And I have this general method which can determine this key relationship. This was the key relationship here between the roots. And now I sort of exploit that relationship and claim that it holds also when the roots are equal to each other. Okay, this was a 4 times longer and 50% better explanation of this method of adequality, but I forgive you if you are totally unimpressed, because it seems we've just done a lot of Algebra 1 in a lot of strange ways, and so sort of who cares or something. Before I erase all this, I'd like to remark that there is something very mysterious going on between these two. I will just highlight 2 facts. Setting x1 equal to x2 is a very interesting thing to do here. And also dividing by x2 minus x1. This is the kind of thing that should give you pause or maybe even make you panic. And preview that whenever you're doing calculus, you seem to be doing a lot of dividing by 0. And Fermat feels perfectly comfortable, on the one hand, dividing by this quantity, which is non-zero, to derive a general relationship between x1 and x2, but then to claim moments later that that relationship holds perfectly well still when x1 actually is x2. Okay, so this is the kind of thing that bothered some people and didn't bother others. Okay, to really understand this, I think you have to do another problem. And I perhaps made a bad decision with 6 minutes left in class to just sort of throw this little problem at you, and maybe I was a little bit flustered, and I definitely didn't explain it well. I bet few people got it. So, okay, keep watching, and we're going to try to redo what we did in the last 5 minutes of class here, but this time, like, you know, the way math should be done, I think, you know, just live, or writing at least live like this. So, okay, so take some function. This is the kind of thing that Fermat realized now he could do. X cubed minus 4x squared plus 11. Okay, this is just my example that I made up. Okay, and now, says Fermat, my method is more general than just finding the relative maximum of a quadratic. I can find the relative maximum of any polynomial, cubic, quartic, whatever I want. Because I've abstracted away from the geometric interpretation, and or mostly abstracted away from it, there's still some sort of pointing at the picture going on. Okay, so yeah. So now let's make a graph of this, which I did on the packet, but I'll sort of do it again. What does this function look like? Well, okay, up here at 11, you know, it's got a y-intercept, and then it's got a, you know, nice cubic shape. Let's not worry about it too much, but it does this type thing. Okay, that's perfectly fine, I suppose, unless you care about things. Okay, so here's my cubic wonderful. Okay, and let's just mostly not care about the negative inputs and just care about the positive ones. Okay, what am I doing? I am solving. So now to take this function and now consider solving for places where this function equals c. So what is c again? It's this sort of moving target. We sort of begin the problem by we pretend to begin the problem by setting the function equal to c. So here I'll call this c. So that's c. This is just the line y equals c. And indeed, it appears if c is something like 3-ish, but it really doesn't matter. But on the picture I drew it as if it were like 3 or something, that there are going to be 2 points of intersection, x1 and x2. Okay, and I want to find what those points are. Or really, I don't want to find what they are at all. I just want to note that there are 2 of them. Okay, so it's once again this sort of proceeds in two steps. It's step 1 is we sort of pretend to solve the equation f of x equals c. So solve the equation f of x equals c. Observe 2 solutions. Never mind, you know, what they are. Instead of finding the solutions, what I want to find is a relationship between those solutions. Okay, so let's just suppose that the 2 solutions are x1 and x2. This is exactly analogous to so suppose f1 equals c and f of x2 equals c. This is exactly analogous to what we did on the previous problem, but now you should be more impressed because this is new math that no one had ever done before. Okay, well, if these 2 numbers, again looking at the picture, x1 and x2, are solutions to this equation f of x equals c, then what do I know about them? Well, I know 2 things. I know that when I plug them in, when I plug in x1 and I cube it, minus 4x1 squared plus 11, that's going to be c. And I also know that x2 cubed minus 4x2 squared plus 11 is going to be c. And okay, well, if that's true, then I can just set these 2 equations equal to each other. So, x1 cubed minus 4x1 squared plus 11 equals x2 cubed minus 4x2 squared plus 11. Well, of course, I can cancel the 11s, and I can also get the cubic terms over to one side and the quadratic terms over to the other side. So this gives me 4 x2 squared minus 4x1. Well, I guess I can be, this is like a sophisticated audience, right? So I can just maybe take a couple of steps at once here. X1 squared, And then here I get x2 cubed minus x1 cubed. Okay, so once again I'll try to explain what I'm doing. What am I doing? I have pretended that I was trying to find the points of intersection between this cubic and a line, but really what I'm doing is something sort of deeper. Really what I am doing is I am investigating the relationship between the roots x1 and x2 of the function. I'm investigating the solutions. I'm investigating a general relationship between the solutions. And these solutions are sort of independent of C. Okay, and now you do some algebra that they were getting really good at there. So I factor this into 4, x2 minus x1, x2 plus x1. And over here, we have the difference of cubes formula. So that's x2 minus x1 times x1 squared plus x1 x2 plus x2 squared. Quantity squared, like that. There we go. Okay, and now we do that same move, which is to divide by x1 and x2. And, okay, what do we have? I have 4 x1 plus x2 equals x1 squared plus x1 x2 plus x2 squared. Okay, and now what do I make of this sort of mess? This doesn't really make me happy. I don't understand it. It's not obvious. It has no particular geometric bearing whatsoever. It is just an abstract algebraic relationship between x1 and x2, between the solutions. Okay, well let me just kind of put it in a box and be happy with it, right? Here's what I suddenly know. What I know is that if you give me this particular cubic equation and you seek the solutions to when this function equals some y value c, then those two solutions will have this particular relationship with each other. Okay, and Fermat feels very, very strongly that this relationship simply just holds, right? This is a relationship between x1 and x2, regardless of what c is. Well, now we take our bold step. And the bold step, so now this is next step, minimize c. I want to make c as small as possible. And by making c as small as possible, I can find the relative minimum of this cubic. And so once again, I'll draw a sort of dotted blue line in here to indicate the fact which is obvious to everybody, which is that this cubic, this c will be as small as possible when these two roots x1 and x2 are just on top of each other. And so the claim by obviousness is that that f has a relative minimum when x1 equals x2. Okay, and so set x1 equal to x2, and let's just call that x. But now Fermat leans on this relationship over here, and this relationship is a relationship that holds between x1 and x2. And so he believes that even though he used the fact, you might say, that x1 was not equal to x2 in his derivation, he wants the truth of the derivation he wants the derivation to still hold, even if x1 equals x2. In fact, he doesn't really worry about it at all, even though this is my problem, not his. Okay, now sort of magic happens, right? Because I now reach for this formula, and what does this formula tell me? This formula tells me that the two roots, x1 and x2, have this relationship here in this box. So I'm just calling both of them x now, so I get x squared plus x squared plus x squared all over x plus x. And okay, in modern language, this says that 4 is 3x squared over 2x. And even you can cancel the x's, so 3x over 2. And suddenly we get that x is 8/3. Whoa. That, I think, should sort of be a little bit shocking. I have just found that when x is precisely 8/3, that is the value at which that's the x value at which they have the same value, the two roots. So when you make you find the minimum by making the two roots the same. And just as a quick sanity check, because we all know calculus here, of course with calculus this all becomes trivial once you know all the like formulas and stuff, because calculus is designed so that you really don't have to do any thinking at all about what you're doing. It's all just a big formula party. So you take this derivative and it's just 3x squared minus 8x, and okay, you set it equal to 0, x, 3x minus 8, and boom, there it is. Cha. So that's kind of, I mean, of course there's another 0 where the derivative is 0, there's a relative max up here. But alright, so the modern approach is to use all kinds of fancy calculus theorems, and basically here we have Fermat basically doing essentially derivatives. And okay, well, I wish I had done this live in class, well, and that there was time for it, because I would love to hear some discussion now about this, and whether you find this kind of impressive or not. I think it's quite cool. One more thing going on in this video is that this was all getting kind of hard over here, right? And I feel that if we stick to polynomials, this is going to be, not that difficult. But Fermat wants this method. He calls this thing that he does over here, he calls this adequating, or at least I think that is his word. I'm trying to remember exactly what he uses. Actually, so the method of adequality, I think, more properly speaking, is this extra little twist he puts on it. And this extra little twist he puts on it is, well, I don't really need to call this x1 and x2. Let me just call this x and x plus e, where I think of e as being something really, really small. Okay, so we're going to do one more problem, because if you weren't impressed by that, maybe you will be by this. Because now we're going to find slopes of tangent lines to curves. Something which you might think of as sort of quintessentially calculus. And Fermat was just doing it. So here we go. This should have been probably like page 2 of this packet, but I didn't do it, so I'm just going to draw it now, I guess, is what I will do. Okay, so what's going on? I have some horizontal axis. I have some curve. Maybe I should make my curve in a certain color. So the curve maybe is like this. So that's my curve. And says Fermat, well, choose a particular point on this curve. Let's call the point of interest B. Okay, great. Drop a perpendicular down to this sort of axis that you've established, and call that point C. And yeah, then think of there as being another point F, which is just a tiny bit bigger than B, or a tiny bit farther along the curve. And well, we can also drop a perpendicular from F, and we can call this point I. Okay, and now, we should probably establish some kind of, and then let's make the tangent line. So the overall goal here is to find the tangent line. So let me draw in the tangent line, and then let's sort of speak of the properties that it's kind of supposed to have, and then we will have, by finding those properties that it's supposed to have, then I can come up with some algorithm for sort of knowing what it is. Okay, so that's the tangent line, but okay. And what else? Well, there's some kind of coordinate system going on. So let's suppose I have some other point, D. This is the kind of thing Fermat did. So call this this is like the origin. All right. And if that's the origin, then then we can also add in x, which is like the abscissa. I'll call this x. This is the abscissa. It's just how far the point of interest C is from the origin. So that's x. And okay, then the entire thing is the subtangent. So this is the subtangent. Okay, that's maybe what I want to find. Let's call that subtangent t. And a couple more things going on, which is let's let this point up here be A. This is A, and I'll put it in a dotted line or something like that. So A is the point on the tangent line directly above this point F. Okay, hopefully I'm explaining all this pretty well. I think I am. There's an origin of your coordinate system. There's some kind of curve, this purple curve here. Maybe we want to even call this curve like a little f or something, although Fermat wouldn't have talked about it that way. B is a point on the curve where I want to construct my tangent line. F is a point a little bit farther away on the curve, sort of negligibly farther away. A is the point above F on the tangent line. And C and I are the perpendiculars dropped from D and F. D is the origin. The tangent line will intersect the horizontal axis somewhere, and this whole length, perhaps I should give this a name too. This is E. Okay, so maybe I should write this. So we have sort of tangent BE. We have subtangent CE, and then maybe that's kind of just good enough for now. Okay. All right. Question, what can I say about this tangent line in general? Well, what Fermat wants to do is just call this little thing E. E is meant to represent, a very, very tiny, negligible kind of size number. And the goal is to find the tangent line to the curve. Okay. So, good. Well. Here's the thing. A is pretty much just F, right? This is the key idea. That as long as I is negligibly close to C, then A is negligibly close to F, because that's kind of what tangent lines do. They're pretty close to the curve. And okay, so that's kind of nice. And so now I'll just say this is true, when E is pretty much 0. And so what do I want to say next? Well, then there's sort of a pair of similar triangles here. The similar triangles are triangle AEI is similar to triangle BEC. Okay, because they both have this angle here, and they both are right triangles. So that part is totally uncontroversial. And okay, so what's therefore true? Well, then AI, I can say, is to BC, as EI is to EC. Okay. In other words, using some of this kind of modern language and notation, what is AI? AI is well, AI is actually, I don't quite know what that is, but AI is pretty much AF. So now maybe that's the thing to do. So since AI is pretty much just AF, then let me say that the previous line holds exactly, but now this line holds kind of like approximately. So here, what I have done sort of here is I use the fact that A and F are pretty much just the same thing when I made this substitution here, AI for AF. Okay, and so, well, what is AF? It's basically just the value of the function. AF is basically just f of x plus e. And BC is actually just f of x. That's just the height of the function at x when you're x away from the origin. And what's EI? EI is x plus e. And x, and then EC is just What? Oh, no, I don't want to say x plus e. That's actually just wrong. EI is not x plus e. EI is t plus e. T plus e, yeah. And EC is t. Okay, so they did it all in terms of the subtangent. Okay, and so, conclusion, says Fermat, you know, f of x plus e times t is t plus e times f of x. Okay, and so you might be thinking, what's going on here? What can I be doing with this? Well, all right, let's take a particular example. So, example, for our purposes, let our function be like root x. So let f of x be root x. Okay. Great. Then what does this tell me? It tells me, and maybe I should continue to be writing approximately's here, because that is really what we're doing. Well then, using this derivation that we did in general for this particular problem, then what this says is that root x plus e times t is approximately equal to t plus e times root x. Okay, great. Now what? Well, square both sides of this approximately to get rid of these square roots, of course. So this gives me t squared x plus e is approximately equal to x times t squared plus 2et plus e squared. Okay, so I get xt squared plus e t squared is approximately equal to xt squared plus 2e tx plus xe squared. Kind of even losing track of what's going on myself, but I get some nice cancellation, so that's kind of nice, because these just die. Okay, what's left? Well, et squared is approximately equal to 2etx plus xe squared. Well now I can just divide by e. E, after all, is Fermat's kind of new innovation for e is kind of like sort of the x2 minus x1 after all. Because that's really what b and f are, right? B and F are the sort of 2 points on the curve. And now, just like in the previous problem, what did I do when I wanted to find tangents? I moved those 2 points infinitely close together. But I didn't really phrase it as trying to find tangents, I phrased it as trying to find minima. But it's really the same exact principle applies, right? If I'm trying to find minima, if I'm trying to find tangents, as you know from calculus, you just move the 2 points infinitely close together. So Fermat's innovation for moving points B and F infinitely close together is to just represent the difference between them with some letter E, and then let's make E really small. But before we make E really small, let's divide by E, because that's just algebra. Who doesn't trust algebra? So 2tx plus xe. And well, now we just agreed that E was negligible, so let's just throw out the E's, and they're gone. Okay, so this, we say, is basically 0, so that's just gone. And now that that's gone, I just have this happy little equation, t squared, which is approximately 2tx. Well, now I can divide by t, and I get that t is approximately 2x. Alright, and this was the goal all along. This was apparently something that was famously known to Apollonius or something like that. That the subtangent to the parabola at any given point is double the abscissa. Okay, so contrary to my very, very bad picture here, well, I can just fix it by changing my point D, I guess. Well, I guess this picture isn't bad because the picture was drawn generically, not necessarily with square root x in mind. So I take it back, my picture was fine. But if we now attempt to really draw this well, we find that, okay, oh, that's not going to be well. We find that the square root function, that could be worse. If you take it at some particular distance, x, then you go up here to the curve, and then you draw in the tangent line, maybe I should use a different color, like red, that's more visible. Then when you draw the tangent line, cha-cha, this is looking about right, because I forced it to be so, that this is the, that thing t there in red is the subtangent. And fact about parabolas, the subtangent is twice the abscissa. Okay, and putting this into modern terms, how would we put this into modern terms? I guess we would say something like, if that's true, then what? Then this t is in fact 2x, and this is x, and this is, I kind of lost track of what I was doing. If this is x, then what have I shown about the slope of this thing? That's x, and this is root x? Oh yeah. So yeah. So then in modern terms, we would say then that the slope of this tangent is root x over 2x. In other words, the slope is 1 over 2 root x, which is exactly the well-known modern formula for the derivative of the square root function. It's 1 over 2 root x gives the slope of that tangent. But okay, whew, I think this is pretty exciting. I think this shows a bunch of things. One, it shows how the sort of power of these kind of modern techniques. It shows how they were sort of halfway between this world of geometry and algebra. They were using, for the first time ever really, at least the Europeans, they were sort of letting the algebra kind of do the thinking for them. And with this sort of powerful new algebra that they were just kind of rediscovering from the Arabs and from Asia, and rediscovering and making it up a little bit on their own, suddenly they could solve kind of this brand new problem. This was Fermat. Imagine his delight when he's, okay, well this problem actually was known to Apollonius, this parabola, but there's nothing stopping Fermat from using this to find the tangent line to a cubic or something like that. And that's something that the ancient Greeks did not know how to do, and that filled him with a kind of a delight. So all right, so if Fermat could find tangent lines to curves, kind of, you know, what couldn't he do, or something like that, you might ask. To be continued. Goodbye.